Dear students, in this module we will study about the CopeCHE rearrangement, the Claisen rearrangement and the aza-Cope rearrangement. The CopeCHE rearrangement is an extensively studied organic reaction involving the 3,3 sigmatropic rearrangement of 1,5-dienes. It was developed by Arthur C. Cope. For example, 3-methyl 1,5-hexadiene heated to 300 degrees Celsius yields 1,5-heptadiene as shown in the reaction. The CopeCHE rearrangement causes the fluxional states of the molecules in the bulavalene family. Although the CopeCHE rearrangement is concerted and pericyclic, it can also be considered to go via a transition state that is energetically and structurally equivalent to a diradical. This is an alternative explanation which remains faithful to the uncharged nature of the CopeCHE transition state while preserving the principles of orbital symmetry. This also explains the high energy requirement to perform a CopeCHE rearrangement. Then we will study about Claisen rearrangement. The Claisen rearrangement, not to be confused with the Claisen condensation, dear students, is a powerful carbon-carbon bond forming chemical reaction discovered by Rainer Ludwig Claisen. The heating of an allyl vinyl ether will initiate a 3,3 sigmatropic rearrangement to give a gamma delta unsaturated carbonyl, as can be seen in the diagram. Discovered in 1912, the Claisen rearrangement is the first recorded example of a 3,3 sigmatropic rearrangement. The Claisen rearrangement is an exothermic reaction with an energy of about 84 kilojoules per mole. Concerted pericyclic reaction which, according to the Woodward-Hoffmann rules, shows a suprafacial reaction pathway. Crossover experiments eliminate the possibility of the rearrangement occurring via an intermolecular reaction mechanism and are consistent with an intramolecular process, now understood as a 3,3 electrocyclic reaction. There are substantial solvent effects in the Claisen reactions. More polar solvents tend to accelerate the reaction to a greater extent. Hydrogen bonding solvents give the highest rate constants. After this, we will study about aza-Cope rearrangements. The aza-Cope rearrangements are examples of the heteroatom versions of the CopeCHE rearrangement, which is a 3,3 sigmatropic rearrangement that shifts single and double bonds between two allylic components. In accordance with the Woodward-Hoffmann rules, thermal aza-Cope rearrangements proceed suprafacially. Aza-Cope rearrangements are generally classified by the position of the nitrogen in the molecule. The first example of an aza-Cope rearrangement was the ubiquitous cationic 2-aza-Cope rearrangement, which takes place at temperatures 100 to 200 degrees Celsius, lower than the CopeCHE rearrangement due to the facile nature of the rearrangement. The facile nature of this rearrangement is attributed both to the fact that the cationic 2-aza-Cope is inherently thermoneutral, meaning there is no bias for the starting material or product, as well as to the presence of the charged heteroatom in the molecule, which lowers the activation energy. Less common are the 1 aza-Cope rearrangement and the 3 aza-Cope rearrangement, which are the microscopic reverse of each other. The 1 and 3 aza-Cope rearrangements have high activation barriers and limited synthetic applicability, accounting for their relative obscurity. To maximize its synthetic utility, the cationic 2 aza-Cope rearrangement is normally paired with a thermodynamic bias towards one side of the rearrangement. The most common and synthetically useful strategy couples the cationic 2 aza-Cope rearrangement with a manic cyclization and is the subject of much of this article. This tandem aza-Cope manic reaction is characterized by its mild reaction conditions, diastereoselectivity and wide synthetic applicability. It provides an easy access to acyl substituted pyrrolidines, a structure commonly found in natural products such as alkaloids, and has been used in the synthesis of a number of them, notably strychnine and quinine. Larry E. Overman and co-workers have done extensive research on this reaction. The aza-Cope rearrangements are predicted by the Woodward-Hoffman rules to proceed suprafacially. However, while never explicitly studied, Overman and co-workers have hypothesized that, as with the base catalyzed oxy-Cope rearrangement, the charged atom distorts the sigmatropic rearrangement from a purely concerted reaction mechanism, as expected in the Cope rearrangement, to one with partial or diradical dipolar character due to delocalization of the positive charge onto the allylic fragment, which weakens the allylic bond. This results in a lowered activation barrier for bond breaking. Thus, the cationic aza-Cope rearrangement proceeds more quickly than more concerted processes such as the Cope rearrangement. So, after studying this module, you shall be able to know what are sigmatropic rearrangements, learn mechanism of Claisen, Cope and the aza-Cope rearrangements, identify stereochemistry of Claisen and Cope rearrangements, evaluate variation of Cope rearrangements, aza-Cope and oxy-Cope rearrangements. Analyze and appreciate the synthetic utility of 3,3 sigmatropic shifts in synthesis. By the introduction, sigmatropic rearrangements are pericyclic reactions defined by the migration of a sigma bond adjacent to one or more pi systems, with the pi systems becoming reorganized in the process. In the reaction, the total number of sigma or pi bonds does not change, as the reactant and the product have the same number of bonds. These reactions are intramolecular in nature and generally do not require a catalyst for their completion. Sigmatropic rearrangements are classified based on an order which is expressed by a set of 2 digits in brackets I and J. These numbers are determined by counting the atoms over which each end of the sigma bond has moved. Each of the original termini is given the number. The aliphatic Claisen rearrangement and Cope rearrangement are 3,3 sigmatropic rearrangements. The common feature of all 3,3 sigmatropic rearrangements is a 6-member transition state with a delocalized electronic structure. In Claisen rearrangement, an allyl vinyl ether is converted thermally to an unsaturated carbonyl compound, while in CopeCHE rearrangement, a 1,5-diene is rearranged or it isomerizes. These rearrangements usually require high temperatures in the range 100 to 350 degrees Celsius, although examples of catalytic synthesis are also known. For these reactions, the feasibility of reactions due to stereochemical constraints is governed by the total number of pi electrons present in the substrate. If the total number of pi electrons is 4n plus 2, then suprafacial pathway is allowed, and if the total number of pi electrons is 4n, then antrafacial pathway is allowed. Claisen rearrangement. Claisen rearrangement was discovered in 1912 and is the first known example of a 3,3 sigmatropic rearrangement. The reaction is an important method for carbon-carbon bond formation and is of significant synthetic value. An example of aliphatic Claisen rearrangement where a substituted allyl vinyl ether undergoes 3,3 sigmatropic shift to give a ketone product is shown. The rearrangements are stereoselective in nature. Stereoselectivity arises when there is a substituent on the saturated carbon atom next to the oxygen atom. The geometry of the resulting double bond strongly favors the trans or E configuration owing to the preference of the substituent to occupy an equatorial position on the chair transition state as shown. The aromatic Claisen rearrangement reaction was originally discovered by heating up a sample of allyl phenyl ether. The product has the allyl group shifted to the ortho position of the phenol. The intermediate is thought to be the keto form of the substituted phenol. This tautomerizes to phenol to restore the aromaticity of the ring. You can see the reaction. Next, let us talk about retro-Claisen rearrangements. These are known in aromatic substrates. The mechanism of retro-ortho rearrangement was established based on C14 labeling of substrate. This way, even without a substitution, the mechanism was established unambiguously. The Claisen rearrangement usually prefers a chair-like transition state. When the ortho positions have no hydrogen, a second 3,3 sigmatropic migration, that is a CopeCHE reaction, follows whereby the migrating group is restored to its original structure. For Claisen rearrangement, electron donating groups increase the rate of reaction and electron withdrawing groups decrease the rate of reaction. For example, the para-amino compound, which has an electron donating substituent, reacts 10 to 20 times faster than the para-nitro compound, which has the nitro substituent and electron withdrawing group. Lewis acids such as AlCl3 and BF3 are known to enhance the rate of reactions and lower the temperature required to bring about the transformations. The nature of solvent has also been shown to influence rate of rearrangement, where up to 300-fold change in rates was observed when the reaction was run under different solvents. With trifluoroethanol, the rearrangement goes even at room temperature. Terpenoids are among the group of important molecules that are obtained using Claisen rearrangement. Examples of Claisen rearrangements where some important molecules such as fragrant compounds are obtained. In another reaction, the isoprenoid skeleton was obtained using Claisen rearrangement. Some synthetic examples of Claisen rearrangement are as follows. Next, let us talk about the Ireland-Claisen rearrangement. This is a variant of the Claisen rearrangement where allyl ester of a carboxylic acid undergoes the rearrangement instead of an allyl vinyl ether. In the reaction, the ester is first converted into silyl stabilized enolate, which further rearranges at temperatures below 100 degrees Celsius. As a result of this rearrangement, carboxylic acid is formed as a product. The Ireland-Claisen rearrangement thus offers ready access to chain extended carboxylic acids. Now let us talk about CopeCHE and aza-Cope rearrangements. Cope rearrangement is a well-known reaction involving the 3,3 sigmatropic rearrangement of 1,5-dienes. These rearrangements can be performed thermally or photochemically. The Cope rearrangement of dienes has found utility in a number of regioselective and stereoselective synthesis of open ring systems. As you can see, when the diene is symmetrical, the reaction gives a product identical with the starting material, as shown for 1,5-hexatriene in the example. Another example is that of bulvalene, which undergoes multiple degenerate Cope rearrangements and still retains the same structure due to its fluxional nature of the molecule. In bulvalene, the Cope rearrangement changes the position of the cyclopropane ring from 4, 5, 10 to 1, 7, 8. But the molecule could also have undergone rearrangements to put this ring at 1, 2, 8 or 1, 2, 7 positions. Any of these could then undergo several different Cope rearrangements and yet do not change the fundamental structure of bulvalene. This reaction has referred as infinitely degenerate Cope rearrangement. A reverse aromatic Cope rearrangement of 2 allyl 3-alkylidene indolines obtained by Horner, Wadsworth and Emmons olefination of 2-allyl indolin 3-ones with diethyl cyanomethyl phosphonate provided alpha-allyl 3-indole acetonitriles. Some more examples of Cope rearrangement reactions. In the first example, an unusual Cope rearrangement leads to formation of a 9-member cyclic ring. The Cope rearrangement has been utilized to obtain sesquiterpene such as illimol, which is an essential component of galbanum oil, and many others. Next, let us talk about the aza-Cope rearrangement. Similar to the Cope rearrangement, the aza-Cope rearrangements are also 3-3 sigmatropic shifts that are essentially heteroatom versions of the Cope rearrangement, where the rearrangement shifts single and double bonds between 2 allylic components. The thermal aza-Cope rearrangement proceeds suprafacially as predicted by the Woodward-Hoffmann rules. In aza-Cope rearrangement, numbering is based on the location of the nitrogen atom in the molecule. Due to the presence of charged nitrogen atom and thermoneutrality, cationic 2-aza-Cope rearrangements take place at temperatures 100 to 200 degrees Celsius lower than the corresponding Cope rearrangement. This is due to the presence of the charged heteroatom in the molecule, which drops the activation barrier for the reaction. Compared to cationic 2-aza-Cope rearrangement, 1-aza and 3-aza-Cope rearrangements are less common. The cationic aza-Cope rearrangement has been known to proceed via catalysis, which is suggestive of ionic or even diradical mechanism in some cases. In the simplest form, the ionic nature of this reaction allows lowering of activation barrier, thus promoting the reaction. The transition state structures for the reaction. As you can see, the first is a concerted transition state. The second structure shows a dipolar transition state, and the third structure shows a diradical transition state. The synthetic utility of cation 2-aza-Cope rearrangement arises when it is coupled with manic cyclization reaction to produce acyl substituted pyrrolidines. The pyrrolidines are important precursors for natural products like alkaloids. The aza-Cope or manic reaction is a synthetically useful reaction for cyclization. This coupling of cationic aza-Cope and manic cyclization leads to a thermodynamic bias towards a single rearrangement product, since the manic cyclization is irreversible and its product, an acyl substituted pyrrolidine ring, more stable than that of the initial rearrangement. The first step is a cationic 2-aza-Cope rearrangement, while the next step is that of a manic cyclization, resulting in the formation of the product. Next, let us talk about the aza-Cope rearrangement. The aza-Cope rearrangement involves allyl, vinyl, carbenols. These rearrangements also proceed via a cyclic chair conformation. In the first stage, enol derivatives of aldehydes or ketones are obtained, which are unstable. Therefore, they undergo rearrangement immediately and give the corresponding carbonyl compounds. Thermodynamically favorable anionic aza-Cope rearrangements have also been known, which are driven by low activation energy of the reaction. These reactions are stereospecific and take place via a cyclic chair-like conformation. For the reactions, it is known that potassium ions enhance rate of reactions by many orders of magnitude. One of the major applications of aza-Cope rearrangement was found in the synthesis of ambrytone with the intensive musk odor. Finally, there are reactions that involve a tandem Claisen-Cope rearrangement as shown, carried out at 350 degrees Celsius. The aza-Cope manic reaction has numerous advantages in comparison to other methods. The gentle conditions of the reaction aren't matched. Light heating, normally no higher than 80 degrees Celsius, a wide range of solvents and addition of one stoichiometric equivalent of acid. Commonly camphor sulfonic acid, that is CSA, or a Lewis acid. Other routes toward pyrrolidine synthesis cannot compete with the stereospecificity, wide-scale applications in structures containing pyrrolidine derivatives and large scope of possible starting materials. The reaction exhibits high diastereo selectivity and is robust, proceeding even when faced with poor orbital overlap in the transition state. The advantages of the aza-Cope manic reaction have motivated research on the synthesis of the starting materials for the reaction, which split into two main categories: amine addition and iminium formation, and installation of the vinyl substituent. A wide variety of N substituents, R, alkyl and aryl, can be used in the reaction, of some of which affect the stereochemical outcome of the reaction. Vinyl groups are generally limited to those which are either 1,1 or 1,2 disubstituted, that is vinyl with substituents at R1 and R1 R2 respectively, with a wide range of electronic and steric variety tolerated. Let us now summarize. Claisen rearrangement is a 3,3 sigmatropic shift of allyl vinyl ethers in aliphatic as well as aromatic substrates. The rearrangements involve migration of a sigma bond adjacent to a pi bond system, leading to reorganization of the pi bond system. Claisen rearrangements are stereoselective owing to the chair form transition state. Ireland-Claisen rearrangements also involve 3,3 sigmatropic shifts in allyl esteristo, give rise to rearranged carboxylic acids. Cope rearrangement is an all-carbon 3,3 sigmatropic shift in dienes. aza-Cope rearrangements are heteroatom variations of Cope rearrangements that take place at temperature lower than that required for a Cope rearrangement. Cationic Two aza-Cope rearrangements are coupled with manic cyclization reactions to produce acyl substituted pyrrolidines. Oxy-Cope is another variation of Cope rearrangement involving allyl vinyl carbenols, leading to formation of rearranged carbonyl compounds. Claisen and Cope rearrangements, along with their variants, are synthetically useful reactions to give rise to products of commercial value such as the fragrant terpenoids.